Good. Well, thank you very much, everybody. It's lovely to be here in Corsica. What I like about Corsica is that the sun always shines, as we know. Unlike in Oxford, where they have to wait for about a year to take this photograph. And that's why the university likes us to use it on our things. Actually, I'm not sure that this title really fits the presentation, but what I'm going to do is talk a little bit about some of the measurements we've made and talk a little bit about models that might or might not be appropriate, including the CJP model. And I am going to use the C word, but not very much, so don't worry too much. This you all kind of know about, but I suppose the point that I'm trying to make here is that when we design these structures, people will go away and use Paris law, and that's absolutely fine. But of course, Paris law is nothing really. There's no law about it. It's not like Newton's law. It's simply an empirical curve fit to experimental data, and it happens to be a very useful one, which is why it's used. But the trouble is that structures like this don't see kind of regular uniform loading of the sort that we apply in the laboratory. They see variable amplitude loading. And we all know, for example, that an overload, slightly counterintuitively, can slow down the propagation of a crack. So actually, if you're sitting on an aircraft and it goes through a bit of turbulence, you might be sitting there worrying, but in fact you shouldn't be worrying. You should be happy because it's putting some nice overloads into the wing, which will slow down the crack. Well, it's true, but let's hope they found it before they get that. So anyway, but then you get involved with other things, and many of us have got involved with kind of consultancy things and court cases and whatever, and you find that the actual loading seen by the structure is a complete mess, and we don't really know how to deal with that. So we need to go beyond the Paris law and to try and understand what's happening at the crack tip in far more detail. You know, Paul Paris had a good idea 50-something years ago. I wish I had his citation record, but I'm never going to have his citation record. But we need to move beyond it.
And he got the first $1 million grant at Lehigh.
Well, there you go. See, right. So we've done kind of stuff before, and I've been to all three of these previous workshops, and you know, I enjoy it a lot. But we've done stuff like trying to find an experimental stress intensity factor and compare it with the theoretical one. And what you generally find is that the experimental stress intensity factor follows the same kind of slope as the real one, but there's an offset. And if you put an overload in, that offset gets bigger. So
what is on the x-axis?
Oh, sorry, it's disappeared, isn't it? Let me see if I can get rid of that. Was that gone?
To move the table.
No, it's just a wretched. It's because the wretched. Well, look, it's low, right? No. So we're going up and we're coming back, right?
Okay.
Yeah. So this is the theoretical stress intensity factor. It's linear with load. This is what you get from experiment. It kind of goes up like this and it comes down. There's an offset and there's a little bit of hysteresis. So that's basically it. Now, Neil said yesterday that nobody had proved...
Nobody measured the actual load transfer.
Well, all right, nobody... So, you see, Neil doesn't believe that the door is closed unless you can... Unless you can measure the load between the door and the door frame. He doesn't believe the door is closed. So, when he's had a few pints and he walks into a door, you'll know the reason, right? So... anyway, I thought I'd just show these videos. This one here is very, very early work, and it was done by Leslie Fellows, who's now a priest. She got bored with crack closure and she decided to go into the church. I've not listened to any of her sermons, by the way, but So you can't see very much from this, but this was done by Paolo D'Amatos, and this is rather fun because you can actually see something here. Here it come down, and just watch how that goes out of focus. Okay? So I interpret that as the surfaces coming together and moving out of...
This one's better.
oh, that one's better. Okay, fine, there we go. That button there, right. So, yeah, I interpret that as the surfaces coming together and moving out of plane. And so I reckon that's pretty close to measuring load transfer. And of course, you can take displacement measurements here, and you can see that there's no change in crack tip displacement, and that's what's going on in this video here. This was taken, and we're using DIC software to track pairs of points, and what you should be able to see is when it's at the minimum load, this pair here doesn't open up until partway through the loading cycle. So this distance stays the same, and you can analyse that. So I think all these things show clear evidence of the seawork, right? And we can replicate this by careful finite element modelling. However, there may well be other things going on, and if one wants to use shielding as a more inclusive word, then I'm absolutely happy with that, and I'm absolutely happy with the fact that closure may or may not be of any use to us in trying to solve our problem. Now, what we've been doing a bit more recently, and this is really quite fun, is we've got this little loading rig which fits in our scanning electron microscope. So what you can do is you can do a bit of conventional pre-cracking, and this is a very small CT specimen. So you see here, you know that this is 35 millimetres, so it's about 35 millimetres square, a little bit bigger than an inch by an inch. And we pop that in here, and here's the original starter notch, and then we kind of grow a crack a bit, pre-crack it, and then we can keep on cracking it using this little loading stage, and we can take SEM images and we can analyse those and get some rather nice results. And you can see here, this is a typical sequence. Here's our crack. And you can see some bits here which are coming out of the plane. And what we're going to do with this crack is we've been loading at a constant amplitude, and we're just going to put a single overload in. It's quite a fierce overload. I'm not suggesting that this happens on your A380, but it's just something to sort of see what happens. Note the scale here, so this is about 20 microns, so we're kind of looking at 100, 150 microns here. So we're really, really close into the crack tip. And I'm going to just play you this little video, and you can see what happens here. So here we go, here's a conventional load, crack tip's about here. And then put another cycle on, and now we put the overload on, I think. And, yeah, there we go. And then we're doing that, right? So we got rid of the closure now. Crack's certainly open after the overload. But just look again what happens during that overload. Crikey, it's fierce. Yeah? So here we've got this. We've got a bit of closure, I reckon, here. Yeah. A lot of plasticity here. A lot of cracking.
Is that 50% though?
It's about 50, I think.
Are you sure of your sketch?
Actually, it's more. Well, this is going to. This was going to 1.2, and they took it up to, I think, 1.85 or 1. Yeah, so it's about 50%.
What's the material?
It's aluminium, 4% copper, so it's a durable. Okay. So there's an awful lot of things going on there that we're not modelling, right? At this kind of scale. Now you may say, oh, well, this is all in our process zone, and the whole point of fracture mechanics is that we don't need to look at things in this much detail, and that's why. Well, maybe we do, maybe we don't. But I just make the point that these are absolutely fascinating experiments to do. And if you've got a scanning electron microscope, and you can get yourself one of these little loading stages, or you can build yourself one. It's really good fun to play around with. Okay, what do we do with this? Well, we thought, well, we'll just try doing the kind of thing that we've done before, which is we don't bother fitting the full field. Why don't we bother fitting the full field? Well, actually, of course, we're taking displacement measurements. Where are those displacement measurements most accurate? Well, they're along the flanks of the crack, where the displacements are the largest values. Where are they of least interest to us? Well, they're along the line ahead of the crack, where they're 0. So, our view is, yes, of course you can do full field fitting, but really you should be taking a lot of notice of the displacement of these crack tip flanks. And also, has the advantage, it's a lot easier. So what we do is we simply take pairs of points here and here, and we look at their relative displacement, and you can use this using any old digital image correlation software. We tend to use public domain stuff, but we also have 1 or 2 commercial pieces of software as well. And you look at relative displacement, and what you find is that the elastic model suggests that this should be proportional to the square root of r. So what we can simply do is look at this and see whether it's proportional to the square root of r. And we're not perhaps expecting a terribly good fit, because we're so close in to the crack tip. But look what you get. Here, these are different loads, okay? And here you have, we've plotted on a log-log scale r against displacement, and the slope varies a little bit, so it's not always 0.5, but it's actually not bad. So that the elastic fit is quite reasonable up until about 20 microns from the crack tip. Right, now let's talk about. Oh look, the bottom's fallen off. That's helpful, isn't it? So I can get away with it now. Here's your CJP model, and this is taken from their paper. So this is not my diagram; it's their diagram, right? And it's an interesting idea, because what they try and do is they try and model the plastic zone and the plastic wake by adding additional terms to the crack tip field. So this is, in my view, an interesting and a good thing to do. But as somebody who plays about with applied mechanics, there are some things about this diagram that I don't fully understand, or don't seem right to me. Now, Neil can put me right on them, but the first thing is that this Fs here, this is intended to represent shear between the surrounding elastic material and the plastic zone, plastic enclave, and that changes sign between the maximum and the minimum load. But this thing here, Fx, doesn't change sign in this diagram. Well, you may say, oh, well, that doesn't really matter because one of them's perhaps positive and the other one's negative. But maybe that's not a helpful thing. But what they have done, for some reason, is given F a different subscript, and I don't fully understand why they've given it a different subscript, right? So similarly, this thing Fy here, this changes sign and it changes its subscript. And I'm not quite sure what's going on there. This thing FC appears on unloading at some point, and it's supposed to indicate closure. But to me, it seems to be doing the same thing as Fy, right? And the T-stress appears here, up here somewhere, and this doesn't seem to be related to load transfer across this interface, right? So, I suppose my view at the moment, and Neil can put me right on this, or maybe others can put me right on it, is that it attempts to capture these physical phenomena, and that's very helpful, but I don't find it completely satisfactory from as it were, a mechanics point of view. I think there's some issues here that I don't fully understand. I've read the paper several times. So, well, where does this model lead us to? Well, it's quite interesting because this F here, this applied F here, gives rise to what they call a forward stress intensity factor, which is Kf, which is similar to K1. And this thing here, this Fpy, and maybe this Fc as well, give rise to a shielding stress intensity factor, Kr. And this F give rise to a shear stress intensity factor, except it's a jolly strange one, because what you find is, although there's a kind of singularity here, you then get zero shear stress here. So what you're getting is a shear stress on one side of the crack that goes up and has a, as it were, a positive singularity, and on the other side it's got a negative singularity, and those two things cancel each other out at the crack tip, and then you get zero shear stress. And then there's the T-stress. So the CJP model takes those forces and boils them down to a forward stress intensity factor, which we think is similar to K1, a shielding stress intensity factor, which is something to do with the shielding, an Fs that we don't quite know what to do with, and a T-stress that we kind of understand, but we think is a second order term. And the main interpretation seems to be on Kf and Kr. So what I was, I suppose what I was thinking is that you could treat this as a, as it were, as an applied mechanics problem. And what I want to do is draw a free body diagram around this grey area. Okay, so I want to look at the equilibrium of this grey area, and I want to look at some of these forces. Well, physically the forces may reverse on sign, and certainly the changes will be in the opposite direction, but we don't really need to worry about that because our measurements will sort it out. There's no need to assume anything about sign, or that some forces are present at some stages and absent at others. If we concentrate on this free body diagram, we really only need three forces on this interface. We need an Fx here, which is going to be reacted by this Fs, right? Because for equilibrium, you need Fx to equal the sum of these Fs's. And then you need an Fy, which is something to do with both the applied stress intensity, or the applied load, and any shielding loads that are coming onto this. Right? So, and it's this Fy which causes the YY strain, and which we think is going to cause crack propagation. So it's that Fy that we might be interested in. So, what I wanted to do was to analyse my results and to work out the various things in the CJP model and to talk about those. But unfortunately I ran out of time. But fortunately Jose was very helpful to me, and I was looking at his thesis and I saw his results and I thought, oh, that's fascinating, I wonder if I can replot those. And I was about to get my ruler out when I thought, well, I'll just email Jose and see if he's around, and he was, and he very kindly sent me his original Excel spreadsheet. So I was able to play about with these results. And this is how Jose presents his results. They're on the same kind of material and the same kind of geometry, right? But it's a full field fitting, and it's rather a larger field. And basically, he uses the CJP model, and he has a Kf here, right? This is the loading cycle, so we're going to maximum and back to minimum. And he has a Kf here, which starts off as rather different from the elastic value, but then is rather similar to the applied elastic value, and then comes here. And he has a Kr, which is usually negative, which doesn't make much sense on its own, although it can make sense when combined with a positive loading stress intensity factor. So that's that. Jose's results plotted using the CJP parameters. What happens if you try and replot those by using a single k, which is equal to kf plus kr, which is, okay, fine, which is what you get from our reduced model. Well, what you get is something like this. So here's the nominal k, and here is kf plus kr. And what I wanted to do was to compare that with our results. And in order to do that, you have to think about where is your origin for displacements. And our origin for displacements in the DIC is when we have the minimum load. So by definition, our results are always going to show 0k at minimum load, right? So what I did was simply shift these down to 0, right? And we can argue whether that's right or whether that's wrong, but that's what I did. And that gave us black line here, and then the red line is our data. And they fall completely on top of each other. And at that point, I decided it was time to go home, right? Because I didn't want to do anything more, because it was bound to be worse than that, right? So what I think is happening here is you're coming along here, the crack's closed, here it opens, up we go. This is a residual or shielding K, which is making the crack see something different from what it would if it was purely elastic. That's not quite constant with load. It does change a bit with load. And then it comes off. So that's pretty much what I want to say. CJP model's got some interesting ideas, but the main terms seem to be KF and KR. I think the concept of shielding is helpful, but what I want to, the question that's now in my mind is, if we've got it, how do we use it? And in particular, I'm concerned that the DIC measurements are surface only, and actually we need DVC measurements, so we need more of the stuff that Jean-Yves is doing. And just thanks to Jose for being awake and sending me his results, and thanks to the organisers, it's great to come here. And just to say that G. Tong and I found ourselves locked out just before coffee time, and we had a quarter of an hour to spare, so we went down the staircase down here. And if you get the chance, it's really, really nice at the bottom. So.